being recorded.
So, welcome to the BASA seminar, hybrid edition. So, just a few announcements. Clément is happy to take questions throughout the talk, but we may be posting, we may be posting the talk online. So, if you would prefer not to be heard online, you should just type your questions in the chat and I'll read it out. So a bit about the seminar. So the purpose of the seminar is to have academics and representatives from the industry present their work. If you'd like to give a talk, or you know someone who'd like to give a talk, please contact one of the organizers. That's me, Sasha, Kanchana, and Josie. And I'd like to thank Julia, who Josie's taking over from Julia for her tireless efforts in promoting the BASA seminar. A little bit about BASA. Why is it called the BASA seminar? So it's named after Sir Adolf Basser, who donated £50,000 in 1953 to help the University of Sydney build its first computer. This computer was operational by 1956. The name of the computer was Celiac. Why Celiac? It stands for Sydney's version of the ELIAC, ELIAC being the Illinois automatic computer. These computers were arguably the supercomputers of their generation, and the Sydney Morning Herald actually called Celiac the brain. And just by the way, Basser said privately that his donation of £50,000 was his winnings when his horse won the Melbourne Cup. The name of the horse was perhaps appropriately called Delta. It's now my pleasure to introduce our speaker today. Clément Canonne joined us this January as a lecturer. Prior to joining us, he was a postdoctoral fellow at IBM Research. His research is about the theoretical and practical analysis of big data and involves a number of areas, including algorithms, information theory, statistics, and computational learning theory. Clément is active in service in the theory community, and notably, he's the co-organizer of 2 online seminars, one on theoretical computer science and one on the theory of data science. The title of Clément's talk is Resources, Constraints, and Trade-offs in Machine Learning.
Thanks. Thank you, Sasha. Thanks for attending the talk and taking some time for some of you from upcoming deadlines. Before I start, I want to encourage you, if you have any questions and feel comfortable being recorded, please ask either in the chat or directly. I'm happy to take questions online. So my talk is titled Resources, Constraints, and Trade-offs in Machine Learning. This is going to be mostly about theory of machine learning. There's not going to be a lot of practice, although I'm going to mention it. And I'd like to start with a disclaimer. So let's see. Yeah, this is not based only on my work. This is based on works joint or not with various people and co-authors. If you're one of them and I misrepresent your work, or if you're curious about some things I say, please feel free to contact me after the talk or by email. I'd be happy to provide pointers or issue an apology. So that being said, I'm going to start with the question, what do we mean by learning? Or what do I mean by learning here? So let's start with a nice abstraction that I'm sure you're familiar with. So we have data, we want to compute something on the data. So we feed the data to an algorithm or a computer estimator from it, and we get the output. And then we prove something about the output with a finite sample guarantee or asymptotic convergence to something. Let's say you want to estimate a parameter or something. That's the traditional view. And I don't mean that in a pejorative way. This is a very fruitful and useful model, which has been used in statistics, computer science, data science, information theory for a lot of time. So this is very neat. Unfortunately, it's a little bit too neat. So for example, what do we mean by we have data and we feed it to the algorithm? In real life, let's say the data is actually distributed. You all have a cell phone. We have sensors on the ground. Most of us do. So we have various sources of data distributed. They are not all the same. So also this is heterogeneous. So we might have to deal with that issue as well. And what do we mean by we feed it to the algorithm? It's an algorithm. It has to run for some time. We hopefully want to get the answer at some point. So if it's intractable, it's not really great. So we have some time constraints, computational constraints there. But not just that. We might have some communication, think bandwidth constraint. I'm assuming you've all seen the recent flying an helicopter on Mars thing, well, we have some pretty strong communication constraints with Mars, for example. I'm not claiming I deal with that kind of strict constraints, but that's an example. We might have to take that into account. Another issue is privacy, for example, health data, or just sensitive data, private data. Think of the GDPR, for example, in Europe, or just basically you don't necessarily feel comfortable providing all your data to, let's say, Google or any big company I can come up with. So we want to preserve some privacy on the data, and that means something with regard to that arrow going from the data to the algorithm there. The little devil here means two things. First, there can be noise in the data, just measurement error or anything. Something went wrong at some point in the data collecting process. Or it can literally mean an adversary. So some malicious attacker that corrupted part of your data. How do you deal with that? The data is not clean. It can be model misspecification or an actual active attack. We would like our algorithm or output to be robust to this. There are also measurements issues, right? Sometimes you don't actually get the data. Think, for example, of an auction kind of setting where you only observe something if the buyer decides that the price you set was good enough. So you can only get data if you have set a threshold according to some threshold you might not know a priori. Or you could also think of linear measurements, or you can also think of any type of physical measurements you have to make. So the way you access the data is not necessarily, I get all of it. So that's some of that. You also have, I mentioned computational constraints, so time. You also have memory constraints. So if you have a router, for example, or if in the, I'm gonna place a buzzword there, if in the IoT kind of setting, you have strict constraints on the memory of the device. They can't just store arbitrary amounts of data. So you have to deal with limited memory as well. The arrow also is not just one directional. Sometimes you've got an interactive kind of setting where you can iteratively figure out more things on the data. That's, for once, this is a good thing that gives you more power, or could. So we've got all that, and then we've got that question, what do we do with all this? We had that nice abstraction, now we've got all that thrown in the mix, or do we handle all those things? So I wish I could answer that question in this talk. I won't, but I'm gonna address a baby version of that for some of those constraints. And hopefully that will give you some incentive to work on this area or try and figure out more things or contact me and see what's known, those kinds of things. So another important question is, what is the role theory has to play here? Because, I mean, I've mentioned all those things, but in practice, it seems like we're able to do a lot of things. As I mentioned, an helicopter was just flown on Mars, but like routinely your car can give you directions. Machine learning systems are deployed and do a lot of amazing things routinely. In contrast, I'm going to talk about learning the mean of a Gaussian. So there seems to be some kind of disconnect here. So what is the role that theory and theoretical analysis and guarantees have to play in that regard? So as I mentioned, this is going to be about learning the mean of a Gaussian. I'm going to first define the problem, but let's just say I picked this one because it seems really simple. The Gaussian distribution is basically what you learn in Stats 101. It's nice, it has that nice curve. How hard can that be? So let's look at that. First of all, this actually took me an insane amount of time to plot. So, but this is a very basic task. Let's say if you come from a signal processing community or measurement, etc., you have some signal and there is some noise. So you have signal plus Gaussian noise, and your goal is to figure out the signal. So put differently, you've got a signal mu, just think of it as some deterministic quantity. And on top of that, you've got some Gaussian error, like white noise that adds to this. And you want to figure, of course, the mean, which is the true signal. How do you do this? First, why do we care about that? I kind of mentioned the signal processing kind of application. There are other applications. But so I like this quote from someone named Roy Gary from 47, which says that normality is a myth. There never was and never will be a normal distribution. You might also be familiar with the other famous quote, which is all models are wrong, some are useful. first of all, as a quip, I'd like to say that I do not know Roy Gary. So as far as I'm concerned, Roy Gary is a myth, and there never was and never will be a Roy Gary. But beyond that, well, there might not be an actual Gaussian distribution. Maybe the height of people cannot be negative, for example, but it's a useful approximation. Many things are approximately Gaussian. If you spot something that has some kind of bell curve, etc., it might be good to, as a first approximation, model it as a Gaussian and see what you can say. Also, just if you've got many independent sources of noise, they tend to cancel out in such a way, think of central limit theorem, that the result is roughly Gaussian. So it's not completely arbitrary to think of that. It's also, I'd like to say, from a theoretical point of view, it's a good step to start. You might want to start with something simple before going towards the more complex things, right? If you can't, or conversely, if you can't even figure that out, maybe you should stop there and figure out that thing before going further. And as we will see, that already captures a lot of the difficulties that can arise. So that's a good way to abstract those, solve them before, again, going towards the more complicated things. So again, we have that very basic task. You have n observations independent from a Gaussian. Your goal is to learn the mean. So just to be clear, when I say learn, let's say you want to learn it in L2 norm, but that's, yeah. So you want to learn the mean. It's a vector, you want to learn it. And the catch is it's a vector in high dimensions. So think of very high dimensions. I wrote 1 million, but it can even be much more. And then the question is, how many observations do you need before you're able to say anything meaningful? So how large must n, the number of observations you have, be before you can say something, achieve small error in your estimate. Just also, so that I'm completely honest, I'm going to make an underlying assumption there that the unknown mean is not completely arbitrary. You just assume it's not like its magnitude is bounded with something you know. It's a small technical point. Just if at some point something I say seems impossible to you, that's probably because that assumption is even there. That's kind of a side point. So again, we've got this model, something coming from a Gaussian distribution with identity covariance and mean mu. Your goal is to learn the mean mu. The good news is we know how to do that, right? In that nice abstraction I've talked about at first, this is very simple. I'm going to say it's stats 101 again. I'm not sure if it's 101, 102, or 100, but you take the empirical mean. You do the natural thing. You have n observations. You take the empirical mean. The law of large numbers tells you that it's going to converge to the true mean. It's efficient. Like it's not very hard to add stuff and to divide by n. It's simple, and it actually works. And if you want a quantitative statement, there are various ways of doing that, but just compute the expectation, the variance, use Chebyshev, and you will see that as long as the number of samples is roughly comparable to the dimension, then you're good. You can the error starts being small. And that's a lot of data if D is large, but it's not too bad. It's linear in the dimension, and also like, you can't really do better anyways. So you might as well get to terms with that. So okay, we know the answer. What happens with all those emojis I added? How does that change? So that table will be slowly filled during the talk. Let's just say I just added that extra parameter here, the desired accuracy, the error you want to achieve. But as long as the number of observations you have is linear in the dimension and okay, inverse quadratic in the error, then you're good. If you have no constraints. Yeah.
In the central limit theorem, is there any fact related to the fact that n is the
So the basic central limit theorem is not going to tell. Oh, yeah. So the question is whether the central limit theorem actually allows you to make the quantitative statements I said. The basic version will not. It just says no, it converges in various senses. But there are quantitative versions. So for example, the Berry-Essen theorem will give you some quantitative convergence. And you can also just, for the Gaussian case, you can all use various other things. So I mentioned the Chebyshev after computing the variance, which works. Or you can also use the fact that the sum of Gaussians is Gaussians. You divide so that reduces the variance, and then you actually have a Gaussian by itself. So there are ways to quantify it, but yeah, the basic vanilla version of the central limit theorem will just give you something asymptotic. Okay, so without any constraints, this is roughly the sample complexity you need. So what's the data size you need? Now, what if we add some corrupted data here? So I'm going to use corrupted data for either random noise, arbitrary noise, or an actual malicious adversary that comes, look at your data, decides to change arbitrarily some of it. So say you've got 1% of your n observations, you don't know which percent. Up to 1% of your n observations have been arbitrarily corrupted. You don't know which ones, you still want to learn the true mean of the distribution. Can you do that? So here, I'm not sure if it's obvious or not, but you had a nice Gaussian, then something happens in the middle, and at the end, well, there's a little peak on the data that has been moved, so that's going to affect the mean. It doesn't look quite Gaussian anymore, but kind of, so it might be hard to detect. So can you do anything, and how expensive in terms of data is that, and also how expensive in terms of computation is that? So the first thing is, no, you can't use the empirical mean. Think of it as if the adversary or the noise just puts things very far away, so outliers that can arbitrarily shift the mean, which is bad. So that nice empirical estimator just disappears. Well, there's a simple solution. If you think in one dimension, just take the median, right? If you move a small fraction of things, the median is not going to move that much. The median is robust, so that's good. Well, what is the median in high dimensions? I'd like to say just take the median, but there is no unique notion of median in high dimensions. You might take the median coordinate by coordinate. You may take the geometric median. Both these things have a bad dependence on the error. By that I mean that if the adversary can corrupt 1% of the data, that might throw your end estimate up by something that scales with the dimension. So 1% of that data corrupted might end up with an error of like 55%. In the worst case. That's not great. There is one notion of median in high dimension that works though, which is the Tukey median. So that's great. The Tukey median has all you want. It's robust, it's well-defined, etc., etc. It's NPR to compute. It's problematic. Also, it's just NPR to compute. It's also NPR to approximate, so you can't even do that. So then what do we do? Well, maybe not that. And that was a long-standing open question in statistics for up until 2016, roughly, where Daik Nicholas, Kamas, Kane, Lee, Moitra, and I think I missed one, so I'm going to correct that slide, and Stewart, show that you can actually get the optimal error in polynomial time with the right sample complexity. So it's a succession of works. They started by showing something like polynomial in the dimension and then reduced it. So you can actually get robustness with the optimal number of data points and in polynomial time. And I'm a computer scientist, so sometimes I say polynomial time, and you should look at me saying, what exactly does that mean? It's actually practical. It's not just polynomial time. It's actually, it can be made fast. So that's great. So I'm gonna describe this. The idea is, overall, is very simple. It's just, well, if an adversary comes and corrupts the samples in such a way that it throws the mean really off, it has to show somewhere else. It has to show in the second moment. So the covariance matrix will have to show something like, it doesn't look like an identity covariance matrix anymore, or something roughly like that. So what you can do is you compute the empirical covariance, and you do a PCA. You look at all the eigenvalues. If one of them looks really weird, then you project all the data in that direction, and you just throw away the outliers. There should not be outliers. In that direction, there's something wrong, so throw away what looks wrong. And then you repeat. And by doing that, it works. You will not throw away too much data, and you will throw away all the bad data. So you might throw away a bit more, but that's fine. This is a very simple approach. Of course, well, if I remember correctly, the paper is like 80 pages long, so it's not that simple to analyze, but the algorithm is simple and intuitive in hindsight. A lot of things tend to be intuitive in hindsight. So since then, there's been a lot of follow-up work. Well, forget about Gaussians, first sub-Gaussian distributions, then more and more bounded moment assumption. If all I'm saying right now doesn't make sense, it's fine, but it goes beyond Gaussian. There are applications to robust optimization, some practical implementations. I think you can even download some code somewhere and run it. So the upshot is robustness to noise, even adversarial noise, comes for free, both in terms of data and computation. And I just gave that archive identifier. Two of the authors have an actual survey on those recent developments from 2019, which is a good resource for that. So that's good. We have the second line and nothing has changed. So let's go further. Another type of constraint you might be interested in is privacy. You don't want your data to be revealed to the world. That might be bad. And when I say privacy, here I'm going to focus on differential privacy, which is a formalization of that. So my apologies for what's going to arrive, because I have to define this. But think of that as your end observations are sensitive data. You're going to estimate the true mean. You're going to output the true mean, like your estimate of the true mean. Your output should not reveal too much about any particular data point you used, because that would be bad. That would mean that in what you output, there is significant information about some data you used, and this is the sensitive data. Formally, that's captured by differential privacy, which is parameterized by some epsilon that think of it as small, between 0 and 1. And so I'll give a rough definition, not exactly the right one, but a rough definition of that. But think of it as I contribute data to the algorithm. The output of the algorithm is going to be some random function of all the data. Well, whether I contributed my data or not should not affect the distribution of the output too much. So the probability that the output is something should be roughly the same, even if I remove my specific data. So I'm just one data point. So it's not too sensitive to the input data, essentially. And it's quantified by that epsilon. So when epsilon goes to 0, you get a lot of privacy, but then that also means you have very little information in the output, so it becomes kind of useless. Yes.
So I have a question. Does this mean that the output shouldn't depend on changing one single data point? So you might have many, many data points.
Yeah. Yeah. So the question is whether that guarantee is only for one data point, and yes, it is. So the way it's phrased, if I change any single data point, the distribution of the output should not change too much. But that composes, right? So that means if I change 10 data points, it's not going to change too much, and then the too much is like by a factor of 10. If I change everything, you should expect the output to change. But that composes well in that sense. The more it degrades gracefully. So that's the formal definition. And again, think of the smaller the epsilon is, the better privacy you get. So in particular, things should become harder to do. And the implication is, again, given the output Y of the algorithm, you can't infer too much about any particular data point that was in the input. Okay, so now let's go back to how that's done. Typically, you would do that by adding noise to the data or to the output. So at some point, you add some random noise, and that in a controlled fashion, and that will give you some privacy. The issue is you have to calibrate the amount of noise to the sensitivity of the estimator. I'm using air quotes, but that's actually what happens. You just need to define sensitivity. So you do that. That's kind of bad because you don't know what the true mean is. But you have to calibrate the amount of noise to that. So the more uncertainty you have about where the true mean is, the more noise you have to add, and that's going to be very expensive because, of course, the more noise you add, the more data you need to overcome that. So the solution then is just, well, I want to estimate the thing accurately. At first, I have no idea, so I'm just going to get a very, very rough estimate. Why is that good? Well, it's not good really for what I want to do, but it's good enough that it's going to reduce the uncertainty from it could be anywhere to, well, it's going to be in that big chunk of the Euclidean space, but big is smaller than anywhere. So now, second step, I can add some noise again, but less noise because I've got less uncertainty. And then I get a better estimate, and I repeat and repeat until at some point, well, I can add just a little bit of noise and get a very good estimate. So you balance things in that kind of iterative filtering. I'm not sure the picture is that informative, but I like the colors. So you start with a very coarse estimate, and iteratively you refine your estimate by adding less and less noise and getting more and more accurate at each stage. And well, that works. You can get good privacy and optimal error. And again, with pretty much the same data size. That was the result of Kamath, Lee, Singal, and Ullman in 2 different works. And again, I'm sweeping a lot under the rug, but in some privacy regime that is meaningful, privacy comes for free. You don't need to pay a lot more in terms of data size, and it's efficient in practice. They implemented it. It works well. So it's not just a theoretical result again. So let's see what that means in terms of our third line. So it's not exactly the same. There's a second term. When I say it comes for free, just if your privacy parameter is reasonable. So think of epsilon as small, but not as small as the accuracy you want to get. Then the second term is dominated by the first, and you pay pretty much the same thing. So with the same data size as before, yes.
So any relationship between the level of noise you inject with epsilon?
Yeah. So the question is whether the level of noise we have to inject at each step scales with epsilon. Yeah, it's going to be typically the sensitivity. So sensitivity is how much your estimate varies if I change one data point, roughly. So think of that in math term like some kind of Lipschitzness. So you take that and you divide by epsilon. So the smaller epsilon, the more noise you have to add. So for example, if you want to add like exponential noise, the variance is going to scale as sensitivity over epsilon. So yeah, in this case, for example, if I want to ensure, I don't know, privacy 0.2, then the second term is going to pretty much be overtaken by the first, and I get privacy for 3. I pay a tiny bit more in terms of the data I need, but that's pretty much all. So that's good. So far, we've got 2 examples where the constraint leads you to come up with a new algorithmic technique, but in the end, you don't have to pay more. Let's see things where that's not true. So I talked about privacy. It was differential privacy. The setting I talked about is commonly known as central differential privacy. What does that mean? In the previous thing, I gave my data to the algorithm, and then the output of the algorithm needed to be private. Put differently, I trust the algorithm, I just don't trust the world, right? So I give my data to the algorithm does something, we publish something to the world, I want that thing not to reveal too much. Now you might not trust the algorithm to begin with, because the algorithm might be, I don't know, some evil corporation, not necessarily evil, but like not very careful about your private data, or you fear that it's not very secure, etc., etc. So your observations are sensitive data, but you want to be private even against the algorithm, the center that performs the data analysis. That's called local privacy. Why? Because you want to preserve your local privacy, yourself, against the rest of the world. Okay, another big definition, I'm just gonna go quickly over that. Local LDP, local privacy, local differential privacy. Now you want to ensure that the message you send to the algorithm is itself private. This is probably better to understand. You've got a bunch of users. Each of them will send their data in some kind of encoded, compressed, randomized version of it to the central server. And you want that thing not to reveal too much about the actual data they hold. And the implication is even the algorithm cannot learn too much about the data of any single user. So of course, that's a stronger version that implies the previous one, but that's a stronger guarantee. So of course, it's going to be harder to achieve. So again, now the problem is I need to add noise again, but to each data point, not just to the aggregate thing to ensure privacy. And there's no solution. Like you actually need to do that. I wish I could come up with like twists. It's actually, you can actually overcome that and get the same thing. No, you can't really. But a second order problem is we know a bunch of techniques to add that kind of noise well calibrated, or like we have standard ways to perform locally private things, starting with economists okay, I'm probably going to botch the date, but Werner in 64 had something called randomized response, where the goal was to perform a poll, a survey for sensitive data, who does drug versus who doesn't. So there's something, for example, called randomized response. You've got other mechanisms, more recent, things like Google has something called rapport. There's something called Adama response, etc. So we have those standard techniques. But if you use them typically without thinking carefully about your problem, that's going to add too much noise, and then you will need more data, and that's going to be impractical. And here the solution is, well, let's just transform the problem we have, for which we can't just use these out-of-the-box mechanisms because they would add too much noise, let's say, to a simpler problem for which those standard mechanisms can be used. That has two good things. First of all, we don't need to come up with a new way to add calibrated noise in a careful manner. This is already done for us. And also, well, if somebody has already implemented those things in practice and tested in some kind of deployed pipeline, you can just come there and say, okay, now you can also do that. Please do, just add some kind of pre-processing step to that, and you can solve this new task as well. So here, when I say transform the problem, just we had Gaussians. Gaussians are complicated, they're continuous, they're messy, they're unbounded. And what we would be doing is you add some noise and you get the message, you send that to the central server. Well, let's just do something simple. I've got my data point. It's a Gaussian in D dimensions. I'm just going to convert it to bits. So just take the signs of each thing. I had a D-dimensional Gaussian, I've got D bits. Bits are simple. You can just add noise in a simple way to them. They're very bounded. They're very nice to analyze. So just do that and apply one of those standard mechanisms to the output of those things. And that's your message that you send to the server. Everybody does that, and the server does something fancy to aggregate those. Not that fancy, but. And the theorem is, well, you can get actually local privacy with that parameter epsilon and optimal error. And now the data size you need is no longer D, it's D square. There is a price, right? Instead of linear in the dimension, you pay quadratic in the dimension. Local privacy is not free, but also it's provable that you need that. It's not just because the algorithm I just vaguely described to you is actually very bad. No, you can't do better. Yes.
So there's a question from online. So a quick question regarding the solution, transform it to the other problem we know. Is there any specific feature of problems that make them privacy friendly? Or is it still in an ad hoc state, those what we knew?
Yeah, I wish I had a good solution. It's still ad hoc. We are trying to develop some kind of general techniques. We have a few general statements saying, oh, these problems look similar, you can use similar techniques for those. But we don't have an actual nice way of saying, oh, all of those, you can do the same thing, etc. It's still somewhat ad hoc, although the techniques are a bit more general than they used to be. So yeah, here local privacy is not free. The algorithm is still very simple. If I were not too lazy to put it on my slides, I could. It's basically you take your Gaussian observation, you take the signs, now you've got bits, you add some noise, you send that. And that's enough. So then we get this thing. So here I put the 3 parameters in there. You might observe that you do have the D square dependence instead of D. If you think of epsilon going to infinity, which I feel bad just saying, you shouldn't, but for large epsilon, then you will get back some modulo some approximation, the no constraint thing, so it actually makes sense. But yeah, you have a blow-up factor in the data size unit. You could see it in 2 ways. You could see it as, well, I need more data to do the same thing, too bad. Or you could see it as being like, well, if I can't afford that, do I really need local privacy, or is there another notion that's more suited to my needs? So you can see it both ways, but here we have that simple algorithm that achieves this, and we can prove you can't really do better. That's the dependence on those parameters is actually the right one. So that was for local privacy, the first example where we see that there is an actual trade-off between what you're trying to achieve, privacy and accuracy, or equivalently privacy and the data size. Now let's say you have communication constraints. I would like to say again the helicopter from Mars, but there might be some less fancy examples. Because yeah, we have real numbers, right? How does one send a real number? It's not necessarily something that is easy to do. So your end observations are distributed, users, sensors, you name it, and they need to be quantized before they're sent to you. How do you do that? What is a good way to quantize this? So here's the problem. A sample is a vector of D real numbers, and your budget is actually L bits per sample. So you can only send L bits. Think of L as a small number. I don't know, 100. The solution would be, again, do the naive thing, you just keep the signs. That seems reasonable. Now you have bits, that's good. The issue is like, that's still D bits per sample. You still can't send all that, not L. And there's, again, a simple solution. It's just, well, you've got many users. Each of them, you can just group them by D over L groups, by groups of D over L users. And each of them will send L coordinates. D over L times L is D. You reconstruct one sample, then you repeat, etc. So that seems very lossy. That seems also very simple, a bit too simple to actually work. And this, well, it actually does work. And you can also prove that it's the best thing you can do. Again, so I've noticed I'm going a bit fast, so if you've got questions, please ask. But also when I say it's the best thing to do, that comes with all the standard caveats from the kind of theory I do, which is up to constant factors. So you might want, I know constant factors matter in practice, so all those algorithms are very simple to implement. That comes with a nice side effect, which is they're simpler to tune. You have fewer moving parts. But again, when I say it's optimal, I'm thinking roughly of like the dependence on that parameter needs to scale that way, not necessarily, and the constant is exactly 2. Which, yeah.
There's another question. How does the corruption level in the robustness case affect the sample complexity?
Okay, yeah, that's a good question. I completely didn't mention that. So I set the corruption level to 1%, but if you can achieve better accuracy than the corruption level, right? If an adversary can corrupt an alpha fraction of your samples, you will not be able to achieve better than alpha accuracy. Just it's information theoretically impossible. So the guarantee is, if I remember the latest one, is that if the adversary is able to corrupt an alpha fraction of your sample, then you will achieve accuracy roughly alpha up to some, it might be alpha square root log 1 over alpha or something, but like roughly alpha. So you achieve the best accuracy you can achieve, and the dependence will be that 1 over alpha square. Let's see. Yeah. So in the robustness, the accuracy is pretty much the same order of magnitude as the corruption level of the data. Can't really do better. So going back to the bandwidth constraint, we can get L-bit quantization and optimal error, and again that scales as D squared. So again, there is a price. It looks actually very similar to the previous one. That's not quite a coincidence. But the bandwidth constraints are not free, and again, we can prove that you can't do better than that. And again, it's a very simple algorithm that achieves this. I'd like to say that the whole theoretical aspect of the difficulty there is to prove that it's the best you can do, pretty much. So proving a lower bound on what you can achieve. So at that point, we have that full table. I'd like to make a few remarks about it. So no constraints, we knew what it was. It's actually, you can call it folklore, although like there's probably a citation for that. Under the robustness constraint, you can pretty much achieve the optimal, the same thing at no actual price. It's computationally efficient. It achieves the right thing. For privacy, in many parameter regimes, you get the right thing. The same thing, like again, no real downside. If you want that stronger notion of privacy, then it starts becoming more expensive. You have a blow-up factor in the data you need. Yeah.
So the question is about L, and so if L keep increasing,
Oh, yeah.
so I'm not talking about n go to 0, but I'm talking about if n go to say infinity, so we go back to no constraint. So is it there's a threshold such that the d squared becomes back to d?
Yeah, yeah. Again, I'm sweeping that under the rug. So the last two, there is. Let's see. Do I have something to write? Yes. I don't know if that's easy to see or not, but the last two, the correct expression should be something like d squared over alpha square e to the epsilon. What we prove is this. So in particular, when epsilon is small, then you get the epsilon square. When epsilon goes up, and there's like a mean and a max somewhere. So if you take your privacy parameter to be essentially, I think, log of the dimension, then that corresponds to almost no privacy at all, and you get back the real thing. And for the L, for the bandwidth, when L becomes D, then there's again a minimum between that and 1. So at that point, you switch back to the original thing. So the blow-up factor is the minimum of the maximum of D over L and 1. So yeah, you can't just say, oh, I'm actually allowing you to get more communications, more bits to send, so you can do better than the case where you had no constraints. At some point, it's just gonna plateau. That's why I say think of L as a small constant, or like a small number compared to D. So yeah, so we've got all those. For the first two, robustness and privacy, it looks like there is no real downside. You can just throw these constraints on it, and you need more algorithmic cleverness to achieve those. But once you have that, you actually get guarantees that are comparable. For the local privacy and the bandwidth, there is a price, there is a trade-off there. You need to balance things out. So you will need more data, or you will need to, for example, provide less privacy. And that's inherent again. So at that point, I'd like to take a step back on all those things and give some conclusions and discussions, because that was just for again, the simple baby case of learning the mean of a spherical Gaussian in high dimensions. That doesn't seem very, very exciting if you keep hearing about incredible machine learning systems deployed. But first of all, that's a good thing we can learn. Some things come for free given the right algorithm. So robustness, privacy in some parameter regimes, you can actually get that for free. And we've been talking about learning the mean of a Gaussian, but that generalizes, and that's a good illustration of those. In some cases, that constraint actually does not matter, and for some others, it actually does quite a lot. So if you've got local privacy, that's stronger requirement, or if you have some hard constraint on communication bandwidth, then you need more data. And I would say that understanding why and when is important, because if you didn't have that, then, well, you come up with a simple algorithm, give something, it doesn't look necessarily exciting. Should we try to get better algorithms or not? Is it possible to do better? If you don't have that kind of guiding result, well, you might spend a lot of time for and hurting your head by banging it against the wall. Conversely, there are things like, this looks too simple, that seems to work well, but it cannot be right. Well, you can prove it does the right thing. Sometimes the simple thing is actually the right thing to do. Typically, that's harder to prove because you need to prove that complicated things cannot do better. Another direction that I'd like to emphasize is, how do those things combine? I've just given 4 different things: robustness, privacy, local privacy, and communication. Well, what if I have local privacy and bandwidth constraints at the same time? That is a thing. Or what if I want to achieve privacy and robustness? I want to be able to not care about opponents that would corrupt my data, and also provide some meaningful privacy to the users. Can I combine those? Those won't actually come for free given the other. There's actually quite a lot of work on those because the notions look kind of similar, but not exactly. So you might also think of other type of constraints you might, like memory, as I mentioned, or others. So all of that, I basically only gave a tiny insight on a big field, but you've got all of those. And of course, all of that for something, not just Gaussian distributions, right? You might want to handle actual, more arbitrary data. Now, going back to the other point, what role can theory have in there? So I think those examples are actually kind of illustrative. I made those points sprinkled through the talks, but let me summarize them. The first one is we can find new algorithms that turn out to be practical. So for that robustness thing, for example, for a while it was just, well, we've got the geometric median or we've got the Tukey depth, the Tukey median. They are computationally intractable, but we don't know anything better. So maybe that's all we need to do. And well, it doesn't scale well, but oh, well, we're just gonna do like dimension 10 and stop at it, or run for longer. And well, now that we know that, as soon as we knew that theoretically it was possible to get the best of both worlds, which seems maybe counterintuitive, then now it's a very active field of work to get those algorithms, to generalize them, to actually get practical implementations of those. And all that would not have happened without those theoretical breakthroughs. As a side note, I also want to mention that it's been also proven that a large class of algorithms cannot be robust without an exponential time, like running time. So it also guides the kind of things that cannot work. So it's useful in that regard as well. So that's the first step. It can lead the way in some sense. And I can be pretty emphatic about that result because I was not part of it. So that's fine. It also can show what can be achieved, right? Again, for privacy, on its face, you need some trade-off. If I want to provide privacy to the users, it looks like I've got to lose something else. Well, that other result on differential privacy for learning the mean of a Gaussian, but again, that generalizes, shows that no, for like very meaningful ranges of parameters, you get that for free. So you might as well, right? And again, I can be emphatic about that because I was not part of that work, but they also gave an implementation, a practical version of it that runs well in practice as well. A third axis is just also, it tells us when to stop, right? At some point, you have to be, should I keep on trying to get better algorithms and better algorithms? And if you know you can't get better, well, it's good. You can look at something else. It's as good as it gets. Well, either you're satisfied with that or you have to consider a different question or like modify the statement a little bit because you're not going to get better. Instead of just spending another year throwing your resources at nothing. And that brings us to the last point. It helps you identify the bottlenecks. If you've got a big like pipeline, it's good to know what can be improved in it. And well, maybe you should focus on something else than trying to improve that part of the pipeline where like that algorithm is actually, well, again, it's as good as it gets. So don't focus on this. So all those are ways that theory can actually guide, hopefully, practice. I'm not saying it's the end, right? This is always, well, you get those guarantees, then like you need to work more to actually make them work in practice. You need to actually care about the constants. You need to care about the actual details of everything. But those are big, useful rule of thumbs, essentially. So that's pretty much the end. I'd be happy to take any question, or if you have comments on any point. I hope I didn't say anything wrong, and I don't know if any of the people whose work I discussed is in the audience, so we'll see. But yeah, thank you.
Are there any questions from the room or on Zoom?
Sasha, can I ask a quick question?
Yeah, go for it.
Hey, Clément, it's very, very nice talk, very interesting. I have a quick question about the local privacy. Is it because it actually comes from the fact that the non-interactive feature of local privacy? So what I'm saying here is it possible to, like, adding a bit more communication might be helpful to still preserve privacy but enable visibilities? For example, like I mask first, then talk, then demask a little bit, then something like that, right?
So thanks for the question. That's actually a point I didn't even talk about, but that's a good one. So the question was, is that d square blow up? Is it because I don't use interactivity? So in particular, is it conceivable that doing some kind of iterative thing in the local privacy regime, where like I talk to the users, they give me back a message, and I interact with them in repeated rounds? Could that help? As opposed to just them sending me a message and me processing the message they sent. So it doesn't help. It's actually quite interesting here. So we proved that the d square, let me just go back. Yeah, that d square over alpha square, epsilon square, like whatever it is, can be achieved. There is an algorithm that achieves it that is non-interactive. But the lower bound showing you can't do better holds even if you allow like the strongest form of interactivity we know, which is blackboard protocols. If you're not familiar with what blackboard protocols is, okay, that's a whiteboard, so that's kind of a downer, but you just think of all the users speaking at any round in any order until at some point they're tired of speaking. And so they just write their data on the blackboard. Everybody can see it. They do that in rounds, as many rounds as they want, until and at the end, we just call it a day when the server says I've seen enough. Even in that setting, you can't do better than that d square over epsilon square. So we can actually prove that. There are settings for which interactivity can help, but typically not for estimation kind of tasks, or at least not for those ones.
I see. I see. That's very interesting. Yeah, maybe probably I will talk to you more offline for more details. Thank you.
Thanks for the question.
Thanks for the presentation, Clément. Yeah, I have another question, which is about distributed data. So it's like in federated learning, we have different clients, right, and have different data distribution. Mm-hmm. So what we want to say, we want to learn the true mean of the aggregation of the data from our client. Mm-hmm. So the true mean is like the meaning of the mixture of all of the distribution, right? Yeah. So for those results that you presented today, is it guaranteed also for the case of heterogeneous data distribution?
So I'm not familiar with them. I don't know off the top of my head what would be the most relevant result. Yeah, I would have to check. So the question was, what if instead of one Gaussian where all the data comes from the same distribution, I'm more in a setting where I've got groups of users, or each user has a different data distribution. They're still independent. And the mean I want to learn is the mean of the mixture of all those things. So yeah, I don't know. I mean, of course I can, like the lower bound will hold. The thing saying you need at least d square blah blah will still hold, just because a Gaussian is in particular like a very simple kind of mixture. But I don't know if it's actually harder, strictly harder problem or not. Yeah, I'd have to check that. Oh, one last thing I haven't mentioned is also, so I've emphasized that the algorithms are for local privacy and boundaries are very simple. We haven't implemented them, but that's actually something that I'm very keen on doing. And they have another, like the local privacy one has another nice feature, which is it's also communication efficient. It's not, you don't need each user to send a lot of data, they just each send one bit, so like that extra constraint comes for free, which can be appreciable.
Are there any more questions? Okay, well, if not, I'd like to thank, I think we should thank Clément one more time for a wonderful talk. I think besides going from the very small, focusing on just one problem and lots of angles of one problem, he also went all the way to a defense of theory, which I thought was wonderful, and actually gives some support to the quip, there is nothing more practical than a good theory. Thank you, Clément.
Thank you.